Okay, so the pressure head at any point when the fluid flow through the pipe is equal to the pressure, the total head is equal to the pressure head plus the velocity head plus the elevation head. So basically the total head is denoted by the energy grade line. It is basically imaginary line indicating the total head at different locations. And the prismatic head or the hydraulic grade line is basically the sum of the pressure head and the elevation head. So we will create a elevation grade line and hydraulic grade line. For this example, consider a reservoir where the having a water in that reservoirs of infinity level of that much that when water flows to that pipes, the elevation of a water surface is negligible. The change in that elevation of a water surface is negligible. So before find the energy grade line and the hydraulic grade line for any type of a system, we should first assume the datum for that. So this is basically the energy grade line because so at the water surface, basically when the pressure head is zero, when the velocity of a fluid is zero, so here the velocity is mostly is equal to zero, so therefore the energy grade line and the hydraulic grade line is equal to each other. Okay, when the fluid flows to this contraction, the losses occur. So due to the losses occur, mainly the minor losses occur at that point, and major losses is basically when the fluid flow through the pipe and by the contact of water with the side of a pipe, causing the due to the friction of that pipe with the fluid, causing the major losses. So here when fluid flows through this contraction causes a minor loss dropping or causing a dropping of energy grade line at that point. So when the fluid flow through the pipe due to the major losses due to the friction, the energy grade line the energy grade line decreases linearly with respect to the losses occurs when the fluid flow through this pipe. Similarly, when fluids reaches to this contraction, this section, so the energy, the velocity increases due to the velocity increases due to the contraction, the energy grade line drops, and then after decreasing the cross section of a pipe, the losses the losses occurs in this pipe is compared to this pipe. The high diameter of a pipe is higher, therefore is the drop in the energy grade line occurs is a steep slope, showing a steep slope. So at point one, the velocity is zero, therefore the energy grade line and hydraulic grade line will be equal to each other, and the contraction, when the contraction occurs when the fluid through the enter from a reservoir uh, into the pipe, so the drops will occur in energy grade line and the hydraulic grade line, but the difference in between these two will be the velocity head. The difference between the energy grade line and the hydraulic grade line is the velocity head, v square, okay, v square by 2g. So it will show same behavior, but when the pipe, the cross section or the diameter of a pipe decreases, so the velocity increases. So as the velocity increases, the energy the steepness in the slope of energy grade line also increases, and the difference between these hydraulic grade line and the energy grade line also increases due to the increase in velocity. So increasing velocity, so the difference in between these two is basically based on the velocity, v square by 2g. So increasing the velocity, therefore, and in this point, the cross section decreases. So velocity increases. So the difference between energy grade line and hydraulic grade line will also increases. So derive or write a equation for energy grade line or the hydraulic grade line considering the elevation head from that point. from the bottom, from the datum to the uh, water surface of point 1. Similarly, the elevation head up to the point where the velocity is higher of Z2, having also a pressure head from center of a pipe to the energy grade line. Also, the difference in between those two, the energy grade line and the hydraulic grade line, is I mentioned earlier, is equal to the V square by 2G. And this is basically the head loss occurs when the fluid flow through the, or the water flow through the pipe due to the friction between the pipe and the fluid. Similarly for the section 3. So these points should be remembered that the difference between energy grade line and the hydraulic grade line is the velocity head. When the velocity is equal to 0, these two are equal to each other. Energy grade line cannot rise except when the pump is present to add energy. Okay, so I will discuss an example where we will add a pipe in between the pipe to show that how the energy grade line rises when the pump is added in the pipe. For steady flow with constant pipe diameter, the slope of EGL and HGL remains unchanged along the length of a pipe. So as the diameter of for section 2 is constant, so the slope of these two are parallel to each other, or the constant. So for his in a water gym, mostly these four type of equations are used for the calculations of friction when fluid flows through the pipe. The Darcy-Weisbach equation, the Hazen-Williams equation, Manning's equation, and the modified Hazen-Williams equation. So we will discuss it one by one. So first of all, the Pozzilli equation is the mostly we use for the laminar flow, but in case of water supply design, we mostly assume that the fluid or the water flowing through the pipe is showing the turbulent flow. So the Pozzilli equation is equal to the 32 mu LV by rho GD square, or the 32 V nu is basically the kinematic viscosity, and this is basically the dynamic viscosity, or the absolute viscosity, into the LV by GD square. So HF is the head loss, L is the length of a pipe, V is the velocity of a fluid through the pipe, the density, the G, and D square is the diameter of a pipe, and mu is the dynamic viscosity, and nu is basically the kinematic viscosity. And we can also show these equations in term of the flow rate just by putting a value of by deriving the velocity from this equation and putting into this, we can get this equation. For the Darcy-Weisbach equations, when we assume that the fluid is flowing through the pipe in the turbulent flow. So here we can you can see easily that the fluid showing little the variation only at the boundary conditions, and then due to the high velocity, it shows the uniform flow, the steady flow throughout the pipe at the center. So the head loss equations for the Darcy-Weisbach equation for the head loss is equal to friction head loss is equal to the friction friction through the pipe. This is basically the depends on the property of the material by LV by L by D V square by 2G. So by we can also find the head loss or friction head loss in terms of the flow rate just by putting these values, by putting the value of V into the flow equation, Q is equal to AV. So we can get the HF in terms of the V square in terms of the flow. The friction coefficient and the coefficient of friction, this is basically the coefficient of friction is basically depend upon the Reynolds number, the pipe absolute roughness, and the size of a pipe. So that the friction factor in the Darcy-Weisbach equation, this factor can be found by different ways. the Kohler-Brock void formula can be used. This is basically the implicit equations where if you have to find the fraction factor, you have to through different iteration and find the f of for a specific pipe of specific size. You can use also a Modi diagram. I will show that you in the next slide. And for Gen, also derive explicit version of this formula is equal to the fraction factor is equal to 0.25 divided by the log 10 into the pipe roughness coefficient divided by 3.70 plus 5.74 divided by Reynolds number raised to the power 0.9 having a whole square. And for the Reynolds number having a Reynolds number less than 2000 shows the equation. The fraction factor can be calculated by this equation. So we can also calculate the fraction factor for a pipe using a Modi diagram. For the less than the 2000 Reynolds number, we can calculate through this line or this equation. And if we know the relative roughness, pipe roughness of the equation, this is the epsilon divided by d. Epsilon is the material property can be taken from this table by divided by the diameter of a pipe. We can obtain the relative pipe roughness. So by knowing the pipe roughness, the Reynolds numbers, and so we can easily find the fraction factor. For example, if you want to find a fraction factor for a Reynolds number of 10 raised to the power 7, and I have a relative pipe roughness of a 10 raised to the power minus 4, so I will use this line, and yes, drawing a perpendicular on the y-axis, so we can get the fraction factor. So these are the absolute roughness values for different type of pipe material: riveted steel, concrete, cast iron, galvanized iron. So these are the material property in foot and meter. You can use these. So these are the fixed values you can use. You can easily took these values from this table. So this equation basically derived by the Hazen-Williams, known as the Williams equation. So the velocity of a fluid flowing through the pipe is basically is equal to 0.849, where C is the Hazen-Williams coefficient. Is basically is also the material property having different value of for different type of a pipe. R is the hydraulic radius is equal to the area of a pipe and the weighted parameter. The weighted parameter is basically the, for example, if I have a pipe of area A, for example, I consider as a open channel flow through the pipe. So this portion is basically the weighted parameter. So area by weighted hydraulic radius is basically the area by weighted parameter, and while the SF is the friction slope. So for the open channel flow, the friction slope is equal to the slope of a channel bed. But in case of a pipe, it is different than that, because in a pressurized flow, the friction slope is equal to the head loss occurs through the length. So this is equal to the slope of this line of energy grade line. This SF is basically the slope of energy grade line. So this is a L. So ratio of HF divided by L, we get the slope of energy grade line. So these are the Hazen-Williams coefficient, C. Similar, the Manning equation, V is equal to 1 by N, a hydraulic radius raised to the power 2 by 3, and the slope of energy grade line raised to power 1 by 2. And for the US customary units, you have just to replace 1 by the 1.49. And this is the modified form of Hazen-Williams equations, where K is equal to 6.79 when the velocity and diameter in the SI units. So in order to design a pipe, so we should also consider a minor losses occurring through the pipe. So the minor loss is basically occurring due to the pipe entrance when the pipe contractions, expansions, bend, and walls. So these should also be considered in a water in a pipe design. So it basically occurs due to the change in magnitude of a velocity or the direction. When the direction changes, the direction changes basically when we provide, for example, elbow between the pipes. So when the fluid flow through it, the losses occurs. So that type of loss is called minor losses. So by for example, if we have a pipe and we have also a valve in that, and we have also provided a bend and it flows through it. So the sum of we have to sum all of these losses in order to calculate the minor losses. So basically the sum of M is the losses occur due to the walls, to the bends, and other thing, the others stuff provided in between the flow of water through the pipe. So M is basically different for different type of material of different type of appurtenance provided in the pipe, like a glove valve, the angle valve, check valve, the provided a T coupling. So these are different type of fittings which are provided by connecting of different type of diameter of a pipe just by a bend for bending of a pipe, or for maintaining a pressure, providing a valve for maintaining or sustaining a pressure in a pipe. So basically when these are provided, so the losses occurs when the water flows through it. So these should be considered when designing a pipe. So these values basically water gem automatically use these values for the design of any type of pipe. So to simplify, the head losses occurs through the pipe. The Darcy, Weisbach, Hazen-Williams and Manning equation are just simplified in the form of Kp into Qn. Qn is basically depend on the what type of equation you are using. If you are using Darcy, Weisbach and Manning equation, so n is equal to 2. And while for the Hazen-Williams equation, it is equal to 1.852. And while Kp is the pipe constant derived from this equation for the Darcy-Weisbach equation is for this equation used for the Hazen-Williams and similarly for the Manning equations. Similarly, we have also head loss equations having a Km factor can be calculated by these equations and having a Q raised to power n is basically equal to 2. So basically this is the short form of the equation as I showed you earlier. Um, if we solve this equation, so the pi is also a constant, g is a constant, 8 is a constant. So if you calculate this equation, so you get that, you get this equation, this number, this coefficient you get by following these 8 by pi squared g and into the FL by d phi. Okay, let's consider an example of a flow through a pipe. Considering a head of total head of H1 8.1, total head of H2 8.2. So when a pipe flow through, considering also a valve and a pump in between that, having a bend also provided in a pipe. So when a pipe flow through the valve, the minor losses will occur, and when it flow through the pump, it will provided a head. And similarly, when it flow through the bends, so the losses will occur, minor and major losses both will be occur. So let's draw an energy grid line for this example. So considering a total head at H1, when the fluid flow through the pipe, the losses occur, the major losses occurs when the fluid flow through the pipe due to the friction in between the pipe and flow. So when it reaches to the valve, due to the minor losses, the drop in energy grade lines occurs. Similarly, the losses occurs when the fluid flow through the pipe, and when it reaches to the pump. So the pump provided head to the energy grade line or the fluid. So the increasing the energy grade line occurs. So up to that point, similarly due to fractions, losses occurs. The drop in the energy gradient line occurs due to the bend for the pipe, for the bend, and similarly reaches to the total head H2. So writing equation for this energy gradient line, that the total head, so the total head is equal to the losses occur to the friction through all out the pipe. The losses occur to the friction through all out the pipe, and also due to the wall and due to the bend, minor losses. This is basically the losses occurs due to the bend and the wall, and this is basically the HP, the head given by a pump. So this is basically adding a head. Therefore, we are giving a plus sign to it, and is equal to finally equal to the H2. So just plug to the left side. We want to the implicit equation in order to easily solve this equation in Excel. So I will do an example on this. So the fraction losses will be calculated by this equation, while the minor losses will be calculated by this equation. And similarly, the energy head provided by a pump is equal to the input power input given to the pump divided by the unit weight of water into the fluid flowing through the pump. This is basically when the power is provided in the watts, when power is provided in the horsepower. So this equation is basically used. So in order to, this is very important point to be noted, that this type of, this is basically the pump characteristics curve, which is basically provided by the manufacturer. He may provide the pump characteristics curve. He may also provide the data in the tabulated form, and he may also provided the quadratic equation. A quadratic equation for solving the head providing by a pump based on the fluid flowing through the pump. So this is basically the cutoff head. The head provided by a pump is equal to the cutoff head minus the losses occur through the pump. So this is basically the coefficient of loss, and m is the exponent. So m is basically is equal to the 2. So cutoff head is that head when the flow is equal to 0. So this point is basically the head provided. This point is equal to the cutoff head. So this equation may also provided by the manufacturer. So this is very important. We will discuss about the pumps in great detail when we start the case study, because I left that for the case study because it's a little bit complicated topic. So we will discuss that later. So as I discussed the equation, this that the energy equation expresses the total head at one at section 1 H1 minus H2 minus the head losses occur to the fraction, and the head losses occur to the minor losses, and similarly the head provided by the pump. So this is basically the explicit equation. You have to change into the implicit equation by leaving a 0 at one side, so we can easily solve it in Excel. So explicit equations basically can easily be can be easily solved by the Newton methods, like Newton method as we studied in the one was the calculus, another was the, I forget that subject name. So these are the different iterative techniques where we use to solve the explicit equations. Numerical solution. So that is the subject name where we study different type of Rangi-Kutta method and the Newton's method to solve different type of explicit equations by iterative techniques. So considering at this example, we have a length, for example, we have a length of 150 meter, diameter of 0.24 meter, having a fraction factor of 0.02, and also the head provide the quadratic equation, the pump characteristics curve, or the pump characteristics quadratic equation, while the losses occurs, the minor losses occurs is about 5. while the bend minor loss is equal to 0.3. So boundary head, the total head at H1 is equal to 25 meter, and the total head H2 is equal to 40 meter, and the flow direction is given. So to find the flow in any type of a pipe, we should know about the flow. If we don't know about the flow, we can't find the flow through it. So for that, if you don't know the flow, we assume the direction of flow, and based of that assumption, we then find the flow rate through that pipe. So let solve this example in Excel. Are you seeing the Excel file?
No. Yes.
Everyone is
Okay.
okay? Okay. So we know the properties of this pipe, the length, the diameter, the friction factor, and we also know the minor losses occurs through the valve, and also the minor losses occurs to the bend. So the total minor losses occurs is basically the summation of a uh, minor losses through the valve plus two times of bends, because the two bends are occurring in the fluid flowing through the pipe. So by using the minor losses equation, 0.0826 into the sum of minor losses divided by the diameter raised to power 4, we get this value. The This is basically the coefficient of minor losses basically computed by this equation, and based on this equation we can calculate the losses occur to the minor losses occur. Similarly, using this equation, the Darcy-Weisbach equation, we can easily find the pipe constant Kp just by checking these values, the friction factor, the length, and the diameter of a pipe, and then we can calculate easily the head losses occur through the uh, pipe due to the friction. And we have also given a quadratic equations having a coefficient of 50a, b is equal to -5, and c is equal to -10. And we now to find a flow through a pipe, we have to first assume that much of flow is flowing through it, and we have to satisfy this equation, that this equation should be equal to the 0. So we know that h1 h2 just h1 is equal to 25 minus the head losses occur due to the fraction. Similarly, minus the head losses occur due to the minor loss due to the wall, due to the bend, and the head given to the fluid to the flow by the pump, plus the head given minus the total head at point or at section 2. So we have to solve in such a way that the energy equations becomes equals. So we have to just replacing the value to find that until the energy equation becomes equal to, we have to change just the flow. So it's a very time consuming to change one by one to make the energy equation equal to 0. So I will do that by goal seek in order to solve easily. What if So we can use a goal seek tool in easily to calculate the that how much flow is flowing through the fluid. So by setting this cell, you want to set this cell is equal to 0 by changing this value. So it will automatically iteratively changing the flow, the Q value until the cell value or the energy equation become equal to 0. So by directly it will solve this equation and we will get the energy equation equal to 0. So we by solving this equation, so the flow is flow rate or the flow occurring through the pipe is equal to the 0.27 meter cube per second. Any question up till now? Are you hearing me? Hello?
Yes, we are hearing you.
Okay, but I'm trying to conclude it in a while. We have some these equations. So other section is also going to over. So usually when we design pipes water supply system, the pipes mainly in series or in a parallel. Okay, just do these two slides and after that we will do that for tomorrow. We'll leave it for tomorrow. So here I'm just neglecting the minor loss occur due to the contraction. When a fluid flows through the pipes in series, so that according to the continuity equation, the inflow of water into the pipe will be equal to the outflow from the pipe. So always in a continuity equation at any junction, we assume that the inflow is a positive and the outflow is a negative. So the flow entering into at point B is positive, Q1 is a positive minus the flow going outside from junction B. So this is basically the difference between these two is equal to the 0. And similarly for the junction 3, the Q2 minus Q3, the difference between the flow through pipe 2 and the pipe 3 should be equal to 0. Okay, sorry. Now I think it will be visible.
Yes, sir.
Okay, so the flow through the pipe in series is basically the flow inflow into the water enter into the system of a pipe we having in series will be equal to the pipe going outside the pipe system. So it will follow or follow the or the prove the continuity equation that the inflow will be equal to the outflow, but the head losses due to the change in the diameter of a pipe will be equal to the head loss through the pipe 1 plus pipe 2 plus the pipe 3. While in case of while pipes in parallel, the head loss at that point will be the head loss for the pipe 1 will be equal to the head total head at H1 HA minus total head HB minus the head losses occur to the this pipe. Similarly for Q3, the pipe 3, and similarly for the pipe 2, you can use these equations. And while the flow at junction A will be equal to the Q plus Q, because it's entering it into this junction and going outside from this junction into the